line down here. And then this part will reflect that. I guess it's moving upwards. And so I'm just going to reflect myself like this. And there's our reflection in the x-axis. Well, I said take some key points and show the image point. So taking the point -4, 3, so that was this one here. The image point is up here, and I'll put that as x, which just becomes -4, 3. If I took -2, 0, well that just stays at the same point, so that's just -2, 0. We'll do the same thing with 0, 3. That's this dot here. We're going to make it down there, so that's 0, -3. And then 6, 3. Well, that just becomes 6, -3. And if you think about what we've done, the x value didn't change, but the y value did. So the x value stays the same, but how did the y value change? Yes, we made it negative. And if you think about what happened here then, what you've just said to me is, what change did you make to the function? Well, we replaced y with -y, and therefore the function just becomes -y equals f of x, or put nicer, y equals to -f of x. And ladies and gentlemen, this represents the reflection in the x-axis. Try investigation number 2 now. Same function. This time let's graph it out where the mirror is the y-axis. So that horizontal line, I guess, gets reflected this way. And that slanted line gets reflected down this way. And there's my graph, a mirror reflection in the y-axis. Taking those same key points, -4, -3, became now +4, -3. -2, 0 became now +2, 0. 0, 3 stays the same. And then 6, 3 became -6, 3. What happened with the mapping notation in this case? Well, we seem to have changed the x value. We kept the y value the same. So therefore, what we did was we replaced x with -x, so that the function notation becomes y equals to f of -x. And this is how we show that something is reflected in the y-axis. Before we go on, let's do a quick summary. What I've just said here is if you compare y equals f of x with y equals to -f of x, so notice the negative sign is outside of the function, you get a reflection in the x-axis, what we did above in investigation number 1. And the mapping notation is just, we keep the x the same, but we change the y's. So a reflection in the x-axis means we change the y values. Similarly, if we compare y equals f of x with y equals f of -x, notice when we put the negative now inside the function, you get a reflection in the y-axis. And the mapping notation in this case, -x, y. Okay? That's reflections, people. So, you feel good about this? I want you to turn the page, and I want you to take a look at these 3 examples. I'd like you to tell me where the reflection is occurring, and then after that, sketch the graph. Okay, and if you need to make a table of values, by all means go ahead and do so. But if you don't, then don't, because it takes time. Alright, why don't you try these on your own? Stop the tape if you can, and come back when you're done. So in this case, I've chosen to do the x first. Then I'm going to take the purple graph and reflect in the y-axis. Oops, I think I made a mistake. This one looks a little bit too low. Two down. My fault. Gotta be more careful, Mr. Lee. So that means that point is different too. It should be up here. That makes more sense. So the final answer is the line in green. Now in this case the order doesn't really matter, because if I did it the other way around, if I did the reflection in the y first then the x, I should get the same thing. Alright? Okay, so if you've done that, let's move on to investigation number 3. This one should be pretty straightforward because I think you did this in grade 11, in Pre-Calc 11, but nonetheless we'll try it again. I'd like you to complete the following tables. I want to see now how putting a number in front of a function affects the graph. We'll do y equals x squared, negative 3, 9, negative 2, 4, 1, 1, 0, 0, 1, 1, 2, 2, 4, 4. Our good old standard parabola. We're going to do y equals to 2x squared, so notice we have to do the exponent part first. Negative 3 squared is 9 times 2 is 18. Negative 2 squared is 4 times 2 is 8. That's 2, 0, 2, 8, 18. Let's plot these on the graph. Lovely. Do the same thing for the half. Negative 3 all squared. Remember, we got to do that first. 9 times 2 is a half. 4 and a half. That's 2 half. Okay. I hope you can do that in your head too. And if not, oh well, you've got the answers now. 4 and a half. Negative 2 is 2. Negative 1 is 0.5. There you go. 2. And once again, if you don't have color, please label your graphs. And then now, after seeing these pictures, answer parts B and C. How can the graph of how can each of the following graphs be obtained from the graph of y equals x squared? Notice y equals 2x squared seems to be you've expanded vertically by a factor of 2, since all the y values got multiplied by 2. And in this case, for y equals 1/2 x squared, you didn't really expand, you actually shrunk, so we call that a compressed, or compression. So I'll say compressed vertically, because all the y values got squished by a factor of 1/2. So in general, what happens here? Well, when the a value, that number a, in front of the function x squared, if it's bigger than 1, we have an expansion. So you're expanding the y values, okay, by a factor of a. And in this case, when it's between 0 and 1, like a fraction here, you are compressing y by a factor, and it's still of a, because in this case a is now a fraction. So knowing all this, let's summarize. In general, comparing y equals to a times f of x with y equals to f of x, you get what type of stretches? Well, what direction are we going in? We're doing it vertically. So vertical stretches. And the mapping notation, we're not changing the x value, but we are changing the y value. We're changing it by multiplying it by the factor of a. And once again, if a is greater than 1, the graph is what we call a vertically expanded by a factor of a, of course. And the other type, instead of being an expansion, it's called a compression. So this is vertically compressed by a factor of a. Okay. Now you might be thinking, hey, Mr. Lee, you forgot one part. You've told me what happens when a is bigger than 1. You've told me what happens when it's less than 1, but still it's bigger than 0. What about everything that's less than 0? Well, if everything is less than 0, please turn the page. That just means that we have now made a negative. Now, did we just learn on page 1 what happens when we put a negative sign in front of the function? I think we did. So, in general, if a is less than 0, you still get this vertical stretch. Okay. So it could be a compression or expansion by a factor of a, but because of that negative, you also get some sort of reflection. And do you remember this is a reflection in which axis? If the a value, which is the thing in front of the f of x function, is negative, if you wrote down a reflection in the x-axis, bravo! So knowing this now, I'd like you to take a look at example number 2. I'd like you to sketch the graph of y equals to negative 1/2 absolute value of x. And once again, what I'd like you to do is compare this with the what I call regular graph of the absolute value, which is y equals to x, and tell me what type of transformations have occurred. So comparing y equals to the absolute value of x to this function, y equals to negative 1/2 x squared, what's changed? Okay, I see that 1/2 factor. So if you're talking about a vertical stretch, you are correct. Which way am I stretching though? Am I expanding or am I compressing? It's less than 1, so vertically compress by a factor of 1/2. So all of the y values get squished by a half. And then we have this negative in front. So that just shows me that this is a reflection in the x-axis. So I'm going to ask you to graph out the original function y equals f of x. That's pretty straightforward. That's that V-shaped graph. And then now I'm going to ask you to sketch out the graph of y equals to negative 1/2 x, or absolute value of x. I'm going to do it in the 2 steps, where I'm going to vertically compress it first by a factor of a half. Now once again, you don't have to do it in 2 steps. If you can do it in 1 step, go ahead and do so. But most of you are learning this for the first time and you don't want to confuse yourself, so don't. Okay. So here's actually y equals to 1/2 absolute value of x. But I don't want that. I want the reflection in the x-axis as well. So I'm going to now go ahead and reflect. Beautiful. So the graph in green is the final answer. Okay. One last investigation for today. We saved the best for last, or should I say the hardest for last. We're going to now complete the following table values for the square root graph. And then notice in this case, what I have changed is the stuff inside the square root. So it's not like the a value that's outside the function. Now we're changing something inside the function. Okay? I'd like you to graph all these out, and I'll do that myself. I hope you can do the same, and then we'll chat about what you see. Notice for the next one here, I'm making a table of values. If x is 8, 8 times 2 is 16, the square root of 16 is 4. When it's 4.5 times 2 is 9, the square root of 9 is 3. 2 times 2 is 4, the square root of 4 is 2. I think you get the picture. 4, 3, 2, 1, 0. We'll do this one. 16, so that's 4. 3, 2, 1. Y equals to 0.5x. Okay. With the graphs, I'm going to ask you, how can each of them be obtained from the original graph? Alright, so how can each of the following graphs be obtained from the graph of y equals root x? Well, for the first one, which is the one in red, notice what happened. And if you were to take a look actually at the table of values, you'll notice that the y value stayed the same, but the x values had changed. Did they get bigger or smaller? They actually got smaller. So in this case, we don't call it an expansion if they got smaller. This is a horizontal compression. Interesting. And notice the x value, 16 now is 8. 9 becomes 4.5. 4 becomes 2. So notice in this case, we compress by a factor of 1/2. And if you take a look at the other one, where it's root 0.5x, notice that we are now taking the blue graph, and if you look at the x values here, it looks like we're doing a horizontal. And if you said expansion, you are correct. By a factor of, and in this case, 16 to be 32, 9 to become 18. How about a factor of 2? So what goes on in general then? Turn the page. I said in general, how is the graph of y equals to the root bx, okay, obtained from the graph of root x? Well, notice in this case, when b is bigger than 1, we've got the special case where it's a horizontal, I guess it's not that special, but horizontal compression by a factor of, I guess it's 1 over b, right? It's opposite. You see the 2, it's 1/2, right? And this one here, we're talking about a horizontal expansion, once again, by a factor of 1 over b. So everything in the horizontal is kind of opposite or counterintuitive of what you think should happen. So in general, if I have f of bx with y equals f of x, you are looking at horizontal stretches. And the mapping notation here is I'm changing the x value, but notice I'm changing it by a factor of 1 over b. So 1 over bx comma y. So you're taking the x value and multiplying by 1 over b. And if b is greater than 1, we found out that this is a horizontal, or the graph is horizontally compressed by a factor of 1 over b. And if b is between 0 and 1, it is horizontally expanded by a factor, once again, of 1 over b. Just like for a, if it's less than 0, when we have b and it's less than 0, something happens. It looks like when we have this case, we just told you that there is a horizontal stretch. By a factor of 1 over b, along with the b being negative. That's a reflection, and do you remember in which axis? If you said the y-axis, you are good. So let's just take a look at a few more examples, and then I think we'll be done for this section. So here's a graph below. It contains this interesting piecewise function. We call it f of x, and I want you to sketch the graph of y equals to f of negative 1/3 x. So we've got that 1/3, and is that a horizontal compression or expansion? Remember, things are opposite with the horizontal. 1 over something means it's an expansion because the factor is less than 1. But, sorry, not the factor, the actual value, the b value. The factor, though, is of course 1 over that. So by a factor of, and if you think it's 1 over b, the b value is 1/3, so that's just equal to 3. So that's why it's a horizontal expansion. So what I'm going to do first is multiply everything by a factor of 3. The x values are multiplied by a factor of 3. 1, 4 becomes 3, 4. 2, 1 becomes 6, 1. 3, 5 becomes 9, 5. And 4, 0 becomes 12. Here we go. And then we've got that negative, so that negative represents a reflection in the y-axis. And what we do with those points is the points that are x's now become negative. So this one stays the same. 3, 4 becomes negative 3, 4. 6, 1 becomes negative 6, 1. 9, 5 becomes negative 9, 5. And 12, 0 becomes negative 12, 0. And there's your graph of y equals to f of negative 1/3 x. Done. Okay, a few more examples here. Number 4 says here we got a graph of a function. We don't know actually what it looks like, but we've told you that it expanded vertically by a factor of 2, then compressed horizontally by a factor of 1/4, and then reflected in the x-axis. So if the equation of its image is in this form, pretty much what I'm saying is find a and b. Well, what does a represent? It represents the vertical part. So in this case here, we know that it's expanded vertically by a factor of 2, therefore a equals to 2, okay, due to that. Well, horizontally by a factor of 4 means that we're affecting the b value, and remember it's 1 over the factor, so 1 divided by 1/4 is just equal to 4. But then we have this thing called a reflection in the x-axis. Now the reflections are always negatives. The question is, where does the negative go? In front of the a value or the b value? And because this is a reflection of the x-axis, it affects the y values. Remember, we're changing the y values from positive to negative. That affects the a, and we need to put a negative in front. So if you want the equation is really y equals to negative 2 f of 4x. And if you're curious about the values of a and b, well, a just is negative 2, b is just equal to 4. Okay. Try example 5 where I switch things around, and then maybe you can do 6 and 7 on your own as well. So why don't you just try these on your own first? You should know all the things you need to know, and then after that, come back and check your answers with me. Go ahead. Here I see a few things. I see a negative, so of course that's a reflection in the x-axis. The 4 talks about the vertical, and because it's a large number, bigger than 1, it's an expansion by a factor of 4. And that 1/5 is a horizontal. And this one is also an expansion. Remember, it's opposite by a factor of 1 over 1/5, which is just 5. And in example number 6, to sketch these things, I'd like you to list out the different things that are occurring. I see 3 separate things that are occurring. And then from there, you can sketch them out individually, or if you want to combine things together, you can. It's up to you. I see first of all this 2, and that's a vertical expansion by a factor of 2. And if I were to do that first, I'm changing all the y values and doubling them. So 3 becomes 6. 1 is just 1. This is 3 becomes negative 6. Negative 2 becomes negative 4. And this is what you see after that 2. Then we have the 1/2, which is a horizontal. Yes, this is also an expansion by a factor of 2. So now I'm going to multiply every x value by 2. Negative 3 becomes now negative 6. And negative 1 is negative 2. 2 is now 4. And 4 is now 8. Oops. That didn't look very good. Okay. Last but not least, we've got this negative. This is a reflection in the y-axis. So I'm changing every x value and making it positive. So this one, which is now negative 6, becomes positive 6. This one, which is negative 2, becomes positive 2. So I'm going to build it up like that. This one down here, which is positive 4, becomes negative 4. And then this one over here, which is, I think, 8, becomes negative 8. 1, 2, 3, 4, 5, 6, 7, 8. You bet. And so your final answer must be the one in green. No, not green. Red. What am I talking about? Red. Colorblind. Mr. Lee's colorblind. Red. Okay. Last example, then we'll be done. Okay. Now, once again, we're looking at things at individual pieces. Next section, we combine everything together. That one's even more scary, but nonetheless, make sure you know section 1.1 and 1.2 well first, then you'll be great for 1.3. Here, I've given you the 2 graphs, okay? The graph of y equals f of x is shown, and its transformation is on the right. So you're starting with the left, and now I'm asking you for the equation on the right. So my question to you is, how have things changed? You might be saying to yourself, well, it looks like it got reflected. Yeah, it did. Reflected in which axis, dear friends? If you said the y-axis, that is great. Now remember, reflection, the y-axis means what? It means you replace x with negative x, or that b value is less than 0. So I'll just write down this instead, or b is less than 0. Good. Now, I can actually do that and see what happens. Okay. This now looks more like the graph on the right, but something else seems to have changed. It seems to have gotten bigger, and I would say a horizontal bigger. So that would be called the horizontal expansion. And just looking at the points here, this point is negative 4, 2, and that's supposed to be now negative 8, 2. So I'm predicting this is an expansion by a factor of 2, which means the x actually gets replaced with the factor of 1 over 2, or b equals to 1 over 2. So combining these things together, what do you think we'll have? Well, y equals to, the a value hasn't changed. What has changed is the b value, f of negative 1/2 x. And that looks good to me. Now, some of you will be thinking, wait a minute, Mr. Lee, didn't we have, instead of reflection in the y-axis, we had a reflection in the x-axis? Because I think the reflection in the x-axis also gives you the same graph. And by golly, you're right. So if you had chosen the x-axis, then your equation would have looked like this, and this only occurs for this particular example, but this answer also makes sense. Because once again, a reflection of the x-axis means you replace y with negative y, and that's why the negative is outside the function. Okay, I hope this last example wasn't too confusing for you. It's time for you to get ready to do some of these questions in class.